If you all would turn, most of you are already, but if you would turn off your microphones, get some nasty feedback sometimes. The lesson from yesterday is on YouTube. If you didn't already notice that in the email I sent this morning, there's a link there. And I will continue to get the lessons uploaded as quickly as I can through the end of probably this week, maybe next week. After that, there will be a delay, just as it'll be today's lesson will be tomorrow afternoon. It hits the internet. So let's see. We started into acids and bases yesterday. And is my pen ready to go? Yep. So we started into acids and bases yesterday, and the observable properties of acids and bases was on yesterday's lesson, which you can see online. And now we get to a part that's a little more difficult, and I'm just going to warn you that I'm going to be explaining this more than you actually need to know. I'm going to be explaining this for the people who are interested in such things. All right, a few of you have your microphones on, and we're getting a little bit of feedback, so if you could turn those off. So, you remember KEQ, K-E-Q, from last unit, I think? What? Remember stuff from last unit? I know. Maybe you remember KEQ. Now we have a specific kind of KEQ, which is KW. The W stands for water. And basically, so remember we talked about reversible reactions, where something reacts and then it reacts back. In the example I gave you, to context, turn the microphone off. The example I gave you to give you some context was N2 and H2. This is not balanced. React to make ammonia, gas, and then they react back to make nitrogen and hydrogen, and this process just keeps going and keeps going and keeps going. Well, it may surprise you to learn. Okay, Grace, there it's off. David Anthony and Wyatt, turn your microphones off. So let me see now. May surprise you to learn that water is constantly, H2O, splitting apart into H plus. Anyone remember what H plus is? And OH minus. Anyone remember what OH minus is? H plus is acid and OH minus is base according to the Arrhenius definition. Remember, acids start with H, bases end with OH. So water is actually literally an acid and a base at the same time. So it neutralizes itself, and that is why water is the definition of neutral. Now, need to point something out to you folks right now. Notice this right here. H3O plus, which you are supposed to remember from your polyatomic ions. It is the hydronium ion. There's a footnote. That's what that little 2 right there is. At the bottom of the page, you can look down. I'm not going to scroll down. But there is this footnote at the bottom of the page that says that for all, what's the saying? For all intent and purpose? I'm not sure I got that right. But anyway, H plus is the same as a proton, is equivalent to, the equivalent sign looks weird when it's going down, a hydronium ion, H3O plus. These three are used somewhat interchangeably, so you should keep that in mind. If they flip from H plus to proton or from H plus to H3O plus or hydronium, they're equivalent. They're used as if they were interchangeable. So it turns out that in this reversible reaction of water splitting apart into acid and base and then neutralizing each other to turn back into water, this is going on constantly. If you've got a water bottle sitting next to you, it's going on in that water bottle. If you've got a can of tea sitting next to you, it's going on in the water of that tea. If you've got milk, orange juice, any place there's water, this is going on all the time. So the equilibrium constant and how we get this doesn't really matter. The equilibrium constant, the concentration of H plus times the concentration of OH minus is always 1 times 10 to the minus 14th. In an acid, it's 1 times 10 to the minus 14th. In a base, it's 1 times 10 to the minus 14th. So that means that if we've got a lot of H plus, that's an acid, then we have to have a very tiny amount of OH minus in order for it to still work out to 1 times 10 to the minus 14th. If we've got a very large amount of hydroxide base, then we have to have a very small amount of hydrogen in order to still work out 1 times 10 to the minus 14th. So we use, whoops, too far. We use the pH scale, and undoubtedly you've all heard of pH. How could you not have heard of pH? I mean, pH for your pool, pH for your shampoo, pH for your deodorant, pH, pH, pH. And by the way, it's always little p big H, always. If it's not little p big H, it's not pH. It's so that is because the P and the H stand for something, which will come down there in a minute. So pH expresses the concentration of hydronium or hydrogen or protons in an aqueous solution. The more hydronium is present, the more acidic the solution is, and conversely, the less hydronium is present, the less acidic it is. So pH 0 is the strongest acid, pH 7 is neutral, and pH 14 is the strongest base. And where in the world does that come from? All right, Causen and Trenton, please turn your microphones off. So that brings us to what pH is. There is pH mathematically. And I'm going to explain this to you If you get it, great. If you don't get it, as long as you can push the numbers in the calculator, you'll be all right. And you can look down. I'm not going to scroll down. We'll get there shortly. I give you the buttons to push to make this work a little later in the note. So as long as you can push the right buttons, you'll be all right. But I am going to explain it to you for those of you who care. So pH, I told you it had to be little p, big H, because P stands for, and I don't know why it stands for this, by the way. It stands for negative log, and H stands for, now this one does make sense, hydrogen. So pH is the negative log of the hydronium or hydrogen ion concentration. So logarithms. Some of you have taken the math where you did logarithms. Some of you haven't. Logarithms are a short way to express a very long range of numbers. Basically, the logarithm is the exponent when you square, cube, quadruple, whatever, something. So 1,000, that's 100. 1,000 equals 10 to the third. So 3 is the log of 1,000. And you know, writing 1,000 isn't all that hard. Writing 3 is a lot easier. And it works really easy with multiples of 10. A billion, would that be 9 zeros? 100,000 million, yep. A billion is 10 times 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 10. So that equals 10 to the 9th. And 9 is a lot easier to write than all of those zeros. Now, the problem is, it works super easy for multiples of 10. But what about everything else? Well, when I was in high school and college, we had the people who knew how to use them used slide rules to figure these out. I have a slide rule someplace, but I never really learned how to use it. And I'm not even really sure where it is. I haven't seen it in years. I think I know where it is, but nonetheless, some of your dads, if they were engineers, moms, if they were engineers, may have slide rules laying around someplace. But most people didn't use learn how to use slide rules. Instead, there would be a table in the back of the book, and you would have to come to the closest place you could. However, calculators now will easily do logarithms for you. So you can take any number and find its log. Now, be aware. There are two kinds of logarithms. There is the base 10 logarithm, which is 10 squared, 10 cubed, 10 to the 2.7, whatever. And that's just referred to as log on your calculator. This is what we will be using all the time. There is also a button on your calculator that says ln, and that's the natural log. Instead of expressing numbers as powers of 10, it expresses numbers as powers of e. E, in case you care, you do not need to know this, is 2.71828 and more. It's like pi. It's a ratio that just keeps repeating. We are not using natural log. Over natural log, it says e to the x because of the e. We are not using that either. We are not using natural log, not using natural logs. Not. So, antilogs. I don't know what that would be, environmentalists or something. Ha ha ha. I'll laugh at the dumb jokes. You can laugh, but I won't know it. Antilogs are opposite of log. In other words, okay, let me get back up here just a minute. So 9 is the log of a million. A million is the anti-log of 10. I mean, of 9. So these two relate to each other. 9 is the log of a million. A million is the anti-log of 9. And again, as long as you can push the numbers in, you should be all right. So 10 to the x is what we'll be using. Many of you have tried to use 10 to the x button for scientific notation several times in the past. That's the EE button for scientific notation, which is a second comma. 10 to the x is anti-log. We will not be using e to the x. Okay. Please tell me you took your calculators home. Didn't take your calculator home, there's probably some online calculator you can use. So finding pH with a Texas Instrument graphing calculator. If you have a scientific calculator, as odd as it sounds, even though graphing calculators are more science-y than scientific calculators, graphing calculators are not called scientific calculators. If you have a Texas Instrument graphing calculator, to find pH, you push this sequence of numbers. Now, notice please that if I have it in a square box, that's the actual key that you push. So that's a key, that's a key, the key on the calculator. If I have it in brackets, that is the number, not hashtag, from problem. And then the enter, I hope it's obvious to you, would be the key on the calculator you push. You have to push them in that order. If you don't push them in that order, yeah, if you don't push those buttons, they'll push your buttons. Copper says hi, by the way. All right, let's see. So same thing for the next one. This is going the other direction. So, okay, this is to find pH. So to find the hydronium ion concentration, you push second log negative pH, enter. Now again, the things in square boxes are buttons on the calculator. pH is the number from problem. And I'm not going to label all the buttons as buttons or keys. If you can't figure that out. Now, if you're stuck without a graphing calculator, and by the way, other brands, I think there must be birds at the bird feeder or something. Copper's all cranky. Oops. If you're stuck without a graphing calculator, and if you have something other than Texas Instrument, maybe it works this way, maybe it doesn't. You'll have to play with it. might have a hard time helping you remotely. If you have a scientific calculator, you'll use this. And these are the numbers from problems. Let's see, to find pH, push, and to find this. And these are the numbers from the problems right there. But hopefully you've got a graphing calculator. Now, if you have any questions that I can help you with right now, there is some kind of a raise your hand button someplace here. I don't think I have it on my panels because I'm the host, but I think you've got a raise your hand button. Now there is such a thing as POH, which does exactly the same thing, except it measures the concentration of OH instead of the concentration of pH, but it is rarely used. I want you to know it exists. You don't have to do much with it. And in fact, it's pretty easy actually, because remember the 14, they have to add up to 14. pH goes 0 to 14. So POH goes 14 to 0. So pH 8 is POH 6 because that adds up to 14. So you just have to subtract 1. 14 minus 8 is 6, but you're not going to have to do that. Don't worry about it. That's just for those of you who are curious about such things. Oh, come on. Doesn't go, then it shoots. All right, notice this. This is one of these things that I just kind of mention. It's pretty simple, and then people forget about it because I just mention it and move on. Acid dissociation constant. It's an equilibrium constant which expresses how well an acid dissociates or ionizes in water. Now, you say, big whoop, so what? Well, it's actually kind of important, because the more an acid dissociates, in other words, breaks into its ions, the higher the Ka, and the stronger the acid will be. So if you have a table of acid dissociation constants, it's super easy to tell without ever having to do any experiments what acid is stronger, what acid is weaker, because the acid that's higher up on that chart, the acid with the larger Ka, will be stronger. So the strongest acids are hydrofluoric, although I have never personally seen hydrofluoric acid. They tell me that hydrofluoric acid is strong enough to etch glass. I don't know that it dissolves it fully, dissolve its way out, but it will start to dissolve glass. And glass is one of the most inert substances there is. Let's see, hydrochloric acid is very strong. That's the acid, believe it or not, in your stomach. And it's also called muriatic acid, and you can buy it at hardware stores for cleaning off aluminum siding after you dissolve it, and other things. I mean, not dissolve, dilute. It would dissolve when you dilute it, but dilute's the word I want. Sulfuric acid is Battery acid in your car battery, that's very strong. Those are the strongest. Nitric acid is another one right up there. I don't know where you would be familiar with nitric acid. Now, let's take a look at these four terms, and then that will be good for today. So we have these terms. Amphiprotic. Substances that can act as either a Bronsted-Lowry acid or base. Okay, either doesn't refer to Bronsted-Lowry, it refers to acid or base. You remember, according to Arrhenius, acids were H plus and bases gave OH minus. But according to Bronsted and Lowry, acids give a proton and bases take a proton. So something that can give a proton or take a proton is called amphiprotic. An example would be, let's see, H2SO4 is sulfuric acid, which is the one in your car battery. Very nasty. I wouldn't go trying to get any out. It's very, very concentrated in your car battery also. But if it gives away just one of these hydrogens, it can become HSO4 negative. So it still has another hydrogen to give. That makes it an acid. But it could take back the second hydrogen that it gave away, and taking back a hydrogen makes it a base. So according to the Bronsted and Lowry definition, this would be an example of an amphiprotic substance, one that it could go both ways. This could give to become SO4 2 negative. So this is an acid because it can only give. According to Bronsted-Lowry, this is an acid. It can only give. According to Bronsted and Lowry, this is a base. It can only take protons. But according to Bronsted and Lowry, this is amphiprotic. It can give to go to here, or take to go to here, a proton. If you don't understand that, memorize the definition and you'll be all right. Okay, we can use this same thing for an example of the next. Polyprotic is an acid which can give more than one proton per acid molecule. So H2SO4 has 2 protons or hydrogen ions to give away. So it is polyprotic. You can get 3 H3PO4 as phosphoric acid, reasonably strong. I'd have no idea where you might use phosphoric acid in everyday life. But it has 3 protons to give away, so it's polyprotic also. All right, indicators. Now these terms are important, don't get me wrong, but people get really confused about indicators, and the term is used more frequently than amphiprotic and polyprotic, at least at lower levels. Chemicals which change color at some pH. Yesterday I told you 2 indicators. Litmus turns red and blue at neutral, pH 7. I guess technically it can't change both colors at the same pH, so changes like at 7.1 and 6.9. But notice this, each indicator has its own color change pH. There are actually scores of indicators. I don't know about scores, but there's lots. So if you have like a pool or a aquarium where you take a little vial and get a little bit of water from the pool or aquarium and then put a drop of something in and it changes a certain color, and you hold that up against a list of colors to see what pH the pool is, that's not just an indicator, that is a mixture of several indicators, because any one indicator only does one color change at one pH. So the indicators, each indicator has its own color change pH. Litmus and phenolphthalein are pH 7 or 6.9 and 7.1 or whatever. There are indicators that change color above 7 and indicators that change color below 7. Last term is buffers. Okay, I'll start with what they do because that is actually what is easier to understand. Buffers absorb either acid or base with little or no pH change. So like there's buffers, there's buffers in your blood so that if you eat a lot of, well, some years ago, there was this kid who every day came to school with a gallon of orange juice. And he would spend the first, I don't know, 2 or 3 or 4 hours of the day drinking this gallon of orange juice. And every day he'd finish it. Wow. It all went squiggly on us. Every day he'd finish it. And then every next day he'd come in with a new gallon. So orange juice is fairly acidic. And your blood can't take much pH change. So he would pump his body full of this citric acid, and the buffers in his blood would keep it neutral, keep the blood at the right pH. But what about if you eat something that's very basic, or something that's the term we use for basic, and you may be familiar with this term, is alkali. So what if he was eating some of the really sour candies? Some of them use acid, some of them use, I think, a base. Well, the buffer in your blood, if you eat a lot of acid, it fixes that, and if you eat a lot of base, it fixes that. It can absorb either way. What is it made of? Buffers are made of, whoops, not cooperating here. Combination of a weak acid and its conjugate base. So I haven't bothered to help you understand conjugate base, and you don't have to know. You just have to, if you just memorize that, you'll be all right. But for those of you who actually care, these are conjugate acids and bases. So, except they're not weak. Sulfuric acid is not a weak acid, and neither is HCl. HCl is an acid because it can give a hydrogen. When it gives that hydrogen, it becomes Cl minus. Well, this is an acid because it can give a hydrogen. According to Bronsted and Lowry's definition, this is a base because it could take the hydrogen back. It could go back to being HCl. So we refer to this pair as conjugates. This is an acid, and this is its conjugate base. And you don't have to know that. That's just for those of you who actually want to know such things. All right, so we'll end here for today. If you have any questions, now's the time to ask. Hopefully, maybe I need to set an alarm now to wake everybody up, eh? All right. Have a good day.